Hi, welcome to Covalent Bonding Part 1. Today we're going to learn how to construct Lewis structures using an understanding of how atoms bond by sharing electrons. When you share electrons, you can either have a single bond, a double bond, or a triple bond. Not all atoms can have double and triple bonds. A single bond is 2 electrons, one from each of the 2 atoms. So 2 electrons in a single bond. A double bond, you'll see 2 lines, each line representing 2 electrons. So in a double bond, there are 4 electrons being shared, 2 from each of the atoms. A triple bond, you'll see as 3 lines. Again, each line representing 2 electrons, for a total of 6 electrons being shared between the 2 atoms, 3 from each. Again, not all atoms can have a double or triple bond. It all depends on what their need is. These are Lewis structures. You will see some electrons that are not bonded, and those are the dots, and then you'll see the ones that are bonded, which are the lines. So these are called Lewis structures. In a Lewis structure, you'll see a couple things. How are those atoms arranged? And they are arranged in a very particular way. There are rules as to how they are arranged. You'll see the covalent bonds as lines. One line is a single bond, 2 lines is a double bond, 3 lines is a triple bond. And you'll see the ones that are not bonded as the dots. Those are called lone pairs, and all electrons always occur in pairs. You'll never have a single dot on an atom, always in pairs. If you look around at all of the structures you see, they all have the non-bonded in pairs. And everything has to have a total of 8, except for hydrogen. Remember, hydrogen is an exception to the octet rule. In this structure, you'll notice that carbon is in the center. Why can't nitrogen be in the center? Why can't chlorine be in the center? Well, in the center goes the least electronegative atom. We know that chlorine and fluorine are highly electronegative, and nitrogen's closer to chlorine, so it's also a little bit more highly electronegative. So if carbon's present, the rule is carbon always goes in the center. You can see down and over to the right, the 2 carbons are in the center. The halogen is on the outside. In the one to the right, the PBr3, phosphorus is in the center and the halogens are on the outside. You'll never see more than one thing attached to a halogen because they only need one more electron. Again, you see chlorine on the outside. It is the most electronegative. It only needs one more electron, so it's only going to be bonded to one thing. It's bonded to the carbon via a single bond. That's 2 electrons. And then you'll see that it has 3 lone pairs on the chlorine, which gives it a total of 8 electrons to fulfill the octet rule. So since it only has the need to have one more electron, it already has 7, it's in group 17, it will only have a single bond. Chlorine and other halogens will never be center atoms. Carbon is in group 14. It has 4 valence electrons, and it has a need for 4 more. Notice that you see 4 lines attached to that carbon. Each line represents 2 electrons. That means there are 8 electrons around the carbon to fulfill the octet rule. Nitrogen is in group 15. It has 5 valence electrons and has a need for 3 more. So you will see 3 lines attached to nitrogen. This one just happens to be a triple bond. It could also be 3 single bonds, or it could be a double and a single, but it still needs to have 3 bonds attached to it. Notice the carbon. Again, it has 4 valence electrons, and it's sharing 4 more for a total of 8 valence electrons. This one is a single bond. This one is a triple bond. A single bond, it's 2 shared electrons. A triple bond, each one provides 3 electrons for a total of 6 shared electrons. If you add those up, you'll notice there are 8 electrons surrounding that carbon. Here's a different situation for nitrogen. In this case, nitrogen has 3 single bonds. And it has what's called a lone pair. Nitrogen has 5 valence electrons and needs 3 more. Notice it has 3 bonds Attached to it, 3 single bonds. Each single bond brings 2 electrons for a total of 6. The lone pair is 2 electrons. So if you add those up, 6 plus 2 gives that nitrogen 8. Here is oxygen. Oxygen is in group 16. It has 6 valence electrons. In this situation, it needs to have 2 more, so it's doing that with nitrogen with a double bond. Again, you can see that nitrogen, you've seen nitrogen with a triple bond, you've seen nitrogen with 3 single bonds, and here nitrogen has a double and a single bond. It still has that lone pair though. Oxygen will also have 2 lone pairs. In this case, it has a double bond. When you write the Lewis dot notation, that will help you to understand how an atom can bond. In this case, we have a double bond, which is 2 shared pairs, which is 4 electrons. And we have 2 lone pairs. So 4 shared pairs is, 2 shared pairs is 4 electrons. 2 lone pairs is 4 electrons to give that oxygen 8 electrons. Now, if we think about where the atoms are located on the periodic table, it will help us understand why they bond the way that they do. Hydrogen does covalently bond. It also ionically bonds as well. We're going to focus first on how it will covalently bond. Hydrogen is the only one of the in the nonmetal section that we're going to focus on. That isn't in the nonmetal section. I misspoke. So hydrogen has 1 valence electron. It's in group 1. So let's draw its Lewis dot notation. It only wants 1 more. You cannot attach hydrogen to more than 1 other atom because it only wants 1 more electron. And that's because, remember, hydrogen only has an s orbital, and s orbitals can hold 2 electrons only. So the only thing that hydrogen can do is bond with a single bond. And depending on where it is in the structure, that single bond could be on the top, the bottom, the left, or the right. Now we're going to go over to group 17. We're just going to look at the top element in each group on the periodic table and then understand that the rest of the elements in that particular group will bond in very similar ways. So fluorine is in group 17, therefore it has 7 valence electrons. Let's show those 7 valence electrons by writing the Lewis dot notation. If you write it properly, the right, left, top, bottom, you'll always see what it should look like. In this case, fluorine has 3 pairs of electrons on its Lewis dot notation and has 1 that's not paired up. That's the only one that's going to form a bond. So the only thing that fluorine can do, because it only wants 1 more to make an octet, is to form a single bond. Again, where that single bond is located is fine. We can shift things around now. But no more than 2 electrons per side. So the only thing fluorine can do is form a single bond. It wants 1. There's only one way that it can get that. Only one way that it can fulfill the octet role. Group 16. 6 valence electrons. Let's show oxygen's Lewis dot notation. Notice oxygen has 2 pairs and then 2 electrons that are not paired. Those become the bonded electrons. The ones that are paired stay as pairs. So oxygen wants 2 more. It has 2 that are not paired up. Those 2 are going to be the ones that bond. There are several ways that oxygen can accomplish this. Remember, it's any combinations of singles, doubles, and triples. Can oxygen have a triple bond? Think about it. How many more does it want? If it only wants 2, can it have a triple bond? The answer to that would be no. It can have a double, and it can have some singles. The only thing we have to focus on is that it wants to obtain the octet to become more like a noble gas. So our single bonds, I'm going to put them in the top and the bottom. You'll see later on we're going to change those a little bit. So now, with each single line being 2 electrons, that gives that oxygen 8, and it will be bonded to 2 other atoms. If oxygen is only bonded to 1 other atom, the other option to get 2 more electrons would be a double bond. So it wants 2 more electrons, and you can see the 2 possible ways that oxygen can obtain those 2 electrons to obtain an octet and to become more like a noble gas. Nitrogen is in group 15. It has 5 valence electrons. If we draw its Lewis dot notation properly, you'll see that it has 3 that are not paired and 1 that is paired. The 3 that are not paired will be bonded. How can we get 3 more onto that nitrogen? What combinations of singles, doubles, and triple bonds can we have for nitrogen? How can nitrogen bond? Well, the simplest thing to do would be to have it with 3 single bonds, and that's what we would see it attached to 3 other atoms. We may only see it attached to 2 other atoms. It still has that lone pair. In this case, for it to be attached to 2 atoms, we still need to share 3 other electrons. Another combination could be a double and a single. What would be the last combination for nitrogen? It wants 3 more. We're going to have 3 ways for it to obtain that octet. The third way would be a triple bond. Any combinations of singles, doubles, and triples that allow that atom to obtain an octet and to become more like a noble gas. The last group we're going to focus on is group 14, and we're going to use carbon as the example. Carbon has 4 electrons. You know from biology that carbon can form these big, huge macromolecules, and it's because of its bonding capabilities that it can do those things. Notice that carbon has no pairs on its Lewis dot notation. Every single one of carbon's valence electrons will be in a chemical bond. It wants 4 more. What combinations of singles, doubles, and triples will allow carbon to obtain those 4 electrons to become more like a noble gas? Think about it for a moment. What combinations of singles, doubles, and triples will allow carbon to obtain the 4 electrons that it needs to obtain an octet? Did you come up with it can have 4 single bonds? That gives it 4 more electrons for a total of 8. Each line represents 2. So it has an octet if it's bonded to 4 other things. What other combinations? Maybe it can have a double and 2 singles. That will give it 8 electrons. What's another combination that will allow it to obtain 4 more? Any combinations of singles, doubles, and triples? How about 2 doubles? Remember, each line represents 2 electrons. That gives it 8 electrons, and it will only be bonded to 2 other atoms. The fourth combination would be a single and a triple. This will also be only bonded to 2 other atoms, but it will obtain an octet. Notice that carbon will never have any lone pairs on its symbol when it is in a covalently bonded situation. There are some exceptions to the octet rule. You copied these down. You should have copied them down the other day. So we know that hydrogen is an exception. It only needs 1 more, so it's only going to have a single bond because it is only has an s orbital. These two, most of the time you're going to see them bonded normally. Phosphorus wants 3 more, sulfur wants 2 more. However, sometimes when it's with something highly electronegative, like a halogen, it does something goofy. For phosphorus, it takes all 5 of its valence electrons and bonds them. So you can see that it has 5 bonds on it. Each bond has 2 electrons, and that will give it a total of 10 shared electrons. Sulfur sometimes, most of the situations, sulfur is going to want just 2. Sometimes sulfur takes all 6 of its valence electrons and bonds them, when it's again something with highly electronegative like a halogen. And it will then end up with 12 shared electrons. We will talk more about those later on in this unit. Thank you for listening.